Hey,
Hello.
I just had a fun interview, run late. So I want to go get a drink here because I'm way behind here. And some more people are piling in and failing out. I guess I'll pause recording. I'm going to start. Oh, here's York. We got enough of a quorum here. I got a late start because I was doing a fun interview. Podcast probably show up in a couple of days or something. Yeah. So I have started recording. Coffee Compiler Club. I think everyone's been here before. You're gonna record it. I'll throw the video up on YouTube, Twitter, whatever within a couple hours. There's topics are compilers and language runtimes and typing systems and GC and concurrency and anything in between. Anything goes. Open mic. Say what you want to say. Reserved right to moderate. Never had to do it. There you go. That's it. Here, I'll open. I've spent all week doing other things. I've hardly touched my own compiler this week. I got consulting's been kicking up more. These guys doing alternative programming theory language things with declarative languages. Have discovered that I've been deep dive into LLVM generated code via Julia, and there are some interesting screw ups going on there. like Julia is not really a systems programming language, and it's being treated as one. And turns out some interesting fails. And I got beaten up by a bunch of tough dentists in their office and couldn't eat for 2 days. And I don't know, I had some other random things happen and my week just slipped away. So there you go. Spent all week doing other stuff or seeing a dentist. Anyone else want to share anything with their life or what they're doing with compilers? I could talk about what I talked on the interview too, which was just how I do development. Emacs versus IntelliJ versus anything else.
That's an interesting way to start.
Yeah,
it's like,
right.
Let's not build it up. Let's go right into it. Yeah, I think I can start because I did spend quite some time on my compiler. I finally got rid of the ability to respond to panics. So in my language, a panic is a fatal error used for bugs and out of memory issues, that sort of thing.
You got rid of the ability to respond to panics.
Yeah, so previously there were two classes of errors you could handle: exceptions and panics. And panics, you could set up what was known as a panic handler. And the way it worked is that by default, a panic would just terminate the entire program. And then when you set a panic handler at the task level, only that task will be terminated, and that handler would run. And the main use case was like logging an error, or it was also used by the unit testing library to test if some code would panic. We basically spawn a task, set the handler, run it, etc. The issue there is that the sort of internals for it were quite messy. And I felt that the sort of pattern it leads to is a pattern that I'm not a fan of, which is people responding to fatal errors within the program. Now, for some fatal errors that I guess could work, but most of them, I think, is no.
What's your recovery strategy on any arbitrary panic?
Right, and so I think I originally introduced it coming from more dynamic languages where you basically have to have some sort of exception logger because they can occur pretty much everywhere. And they're used for pretty much everything. But so over time, I start thinking, okay, panics happen when there are bugs. Let's say a division by 0. Logging that and, for example, restarting just a task or starting a new one doesn't actually make that problem go away. Chances are it'll just keep happening over and over. And at that point, the negative impact of that is basically the same as just restarting the program over and over. With the difference of added complexity of having to support this, and then you end up with a question like, okay, if you have scope guards, for example, or finalizers or whatever cleanup routine you have, should those run when you panic? Because people might be expected that they do.
And what if they panic inside them?
Yeah, and there's issues like what happens when you panic inside a panic handler.
Right. Yeah.
The current answer was it ends up in a infinite loop because of how I implemented it.
Yeah. Fine.
And then I found out that the way the VM implements preemptive scheduling meant that if a task was running in a panic handler and would suspend and then later be rescheduled, it would sort of escape out of part of this panic handling code. Because when it reschedules, it wouldn't check, hey, are we actually panicking? So you could end up where you panic, suspend, resume, panic again, and then it would sort of enter that panic handler anew. And when it would return from that, it would terminate the task, but it wouldn't continue running the previous panic handler. And so there's all sorts of dragons, basically. And my final approach to that was just completely remove the ability to handle them.
Yeah.
And now a panic is just a hard termination of the entire program.
Yeah.
But that did require, changing my testing library to not use panics as much. That meant I had to add support for spawning sub-OS processes.
Right.
So that you can still test panics.
Right.
And it's ended up taking like 2 weeks.
Right.
Because as part of that, I was also like, you know what? My instruction set is currently 190 instructions. That's a bit much because I basically, what some VMs do, they have, a minimal instruction set, and then they use like native functions for everything else. When I initially started on this, I wasn't really sure what you would use to determine, hey, is this going to be an instruction or a native function? So you end up with this sort of arbitrary choice. So I just made everything an instruction. But once I hit 190, it's like, let's get rid of that. And so now it's this mechanism where the instruction set is still like 90 instructions large. Most of that is because I have a separate instruction for all the different integer comparison operations. So it's like an integer lower, greater, etc. And all the others
Do you
are now
give
basically
any help to a developer who is importing a library to say, hey, you've imported a thing that could panic and bring your entire system down?
No, because you kind of end up in sort of the Java exception state where theoretically everything can panic. Like if you do 10 plus 2, that could panic if you're not on a memory. I mean, it doesn't allocate, but perhaps somewhere deep down in the implementation it does. And theoretically it could panic if an asteroid hits the Earth, right? So you end up with this point where if you want to annotate things that can panic, you would end up annotating pretty much everything.
Yeah. I've been thinking about this a bunch. Like Cameron's got a solution, which is to say all the panics are contained within these separate containers, and the containers could be as strong as an OS forced process boundary. But that's your theoretical border, and a panic kills that and you reach that. And I'm in a different zone. I'm looking at, there's a way to do this with typing, and I kind of have a theory that says you can annotate to say, I shall throw no exceptions. But I don't have to announce everywhere an exception throws because you get a divide by 0, but you also get like a range check exception. It's a realistic, hard to catch. It can't prove, compiler can't prove range check won't happen. But if you want to have a bounds check language, you can throw a range check exception. So I want to have a type that says, thou shalt throw no exceptions out of here which means that if you were going to throw, you're going to stop here and convert it to an error, and put some sort of semantics around that, so I could claim, like, I have a compiler boundary, a module boundary, and module boundaries can't throw exceptions across the boundary. You can only throw an error state. And so the module must make its own call how it's going to convert various flavors of exceptions or panics or whatever into an error. And the caller then has the option to figure out, what the hell, I get an error back, but not an exception. And now what do I want to do with the error, right? And maybe that's a stupid idea, and it goes right back to, well, we'll just convert it from, a panic or an exception or an error state to an exception, and back and forth, because I don't want to deal. But there's something there, whereas the deal with panics is there's usually no real recovery except the process away.
Yeah, and that's why I kind of feel like annotating something that might panic is kind of pointless in that sense.
Yeah.
Because there's nothing you can really do with it anyway.
Yeah.
I think
I disagree with that. Sorry, that last statement, the idea that the only thing that you can do when you panic is to throw the process away. I don't know, it feels like if you're going to say that, like, why not also reboot the computer and the data center, right? Like, there's a unit that has to die, but why is it the process?
Okay, because the OS boundary is essentially perfect. The OS boundary will not let memory get corrupted outside of the boundary. So I will claim that you can.
I'll definitely agree for memory corruption. Like,
okay. So
I'm with you there.
Right. So file system corruptions, like just subtle file system corruption, not file system corrupted in the classic way, but I just broke things in the file system in a proper way. I deleted the wrong thing, whatever. That's a different problem. So looking at a process, can I guarantee that some subpart on the left will not trash some subpart on the right, such that when the subpart on the left makes a panic, I know that if I wipe it out, the subpart on the right can carry on without being impacted, other than realizing the left hand got chopped off, right? And now, what is the right way to define that boundary and enforce it? So theory says I can enforce it with strongly typed in a managed language. But I really need to have the software layer be very clear about what it is it can do and what it cannot, or the left and the right hand will have integrated their fingers too tightly. And when the left hand gets chopped off, the right hand's dead too. And that's time to kill a process, right? So for instance, I'm doing complicated data structures. I've got caches going on. They're multi-threaded concurrent for parallel execution, blah, blah, blah. The left-hand side dies mid-cache update. Is the cache structure corrupt? If it is, everyone's dead, right? So how do I guarantee that it is or it is not? And here, I'm taking, oops. Controls is Atlas.
Software transactional memory, of course.
Yeah, here I'm picking up Cameron's solution and saying, if you have a language-defined way that you can turn into a guaranteed you can't cross the boundary way, then yeah, you can cut the left hand off reliably and the right-hand side gets told the left hand is dead. However, the left and right hand are communicating. There's a narrow interface between them. It's some communication channel. The survivor gets told the loser got killed, and the survivor has to decide, is he going to die or live or restart? Who cares? The survivor gets
obviously it worked pretty well for Erlang as well. I mean, the concept.
Yeah. Yes. And so now the question is, if you don't have that kind of separation and you get a panic, is there anything you can do other than assume that everything's blended and the left-hand side is dead, so therefore his blendedness has corrupted everyone else? Java likes to say, yes, we'll throw exceptions perfectly every time, but what really happens is it corrupted and then it threw an exception. And then some of the corruptions, the right-hand side survives, and it suffices to cut it off at a high level, and GC picks up all the pieces because it's memory safe, so garbage collection works. But some of the times the left-hand side corrupted and then died, and the right-hand side will now discover the corruption a little bit later and also die. And you're better off just killing the process. Here's a classic bad example. I am running a hash table, classic Java hash table. I'm running with one writer and multiple readers. It's a hash table. I'm not bothering to synchronize. Occasionally, a reader gets half of a write and throws a null pointer exception, which I catch and I retry the reader. But the memory is not corrupted. Except very, very rarely, a reader decides he wants to resize because the writer is mid-write and has increased things but not changed the load factor, updated the load factor, not changed the table yet. So the reader wants to resize the table, which then has the writer and the reader resizing the table. And now you have two writers resizing the table, and they cooperatively corrupt the table such that you get cyclic links in the linked list pattern. This is a real example that really happened to us. It took us like 2 fucking weeks to diagnose. You now get a cyclic linked list in the hash table. So the transaction that you were running sent somebody down this particular bucket list in the hash table, and he's scanning for a hit, and he never gets to the end because the list is cyclic. So he just runs forever, burning a core, and he times out. So the high-level guy, the main server process decides this transaction is timed out. He burns that thread down with a thread.def, you can't catch me, die now thread. And garbage collection picks it all up except for the corrupted hash table. He restarts the transaction, and a new thread runs in and hits the same bucket and dies the same way. And eventually somebody else hits the same bucket because it's just a bucket and you can hash to it, and they die. Now you have 2 cores burning down this bucket but never making any progress and getting reset as a transaction. But you're handling other transactions just fine. Then you have 3 caught in there, and then you have 4. And then you have 8 and 10 and 20 and 100. And every time you burn a core and it gets caught in the bucket, your server throughput gets lower and lower and lower and lower. And these one transactions are endlessly trying because your correction mechanism is to say, you took too long, I burn you down, I reset you. And ultimately what happens is your server grinds to a halt in a live lock situation where you have 99 threads running down a linked list that's infinite and 1 thread servicing transactions until it also gets caught, and then you ran out of threads in your thread pool and you're dead. So having decided that you corrupted yourself, what is the legit answer that you can get away with unless you have a hard separation between intellectual property pieces that you can cut one and somebody else knows all the boundary that got cut and can validate and can restart across that boundary afresh. So I'm with you at panic should panic.
It's worth mentioning there in this case, like exceptions, wouldn't trigger panic. In my case, there are some facilities that you can turn them into panics, but that's mostly for cases where you have a program that needs to, let's say, read some SQLite database, and it has to exist before the program runs. Like at that point, restarting a subtask doesn't matter. Like the database isn't going to magically exist. Of course, if you can create it, then you wouldn't use a panic. And my stance there is like for code bugs, let's say division by 0, technically it doesn't matter whether you restart the host or the program or whatever, but it's more about, what does it affect? Like a division by 0 doesn't corrupt the OS, for example, it's contained to the program.
It does mean that somebody's doing something and they stopped what they're doing. If they tried it again, they'll probably fail again the exact same way. So they can only get halfway into whatever their action is and then stop. And the question is halfway in corrupt anybody else?
Right.
Yeah, it's about transactionality.
Yeah.
Yeah, and there's things where, you might perform an operation, panic, and then you're supposed to perhaps do some cleanup. And if you don't, that first operation.
You bumped a ref count and you panicked. You bumped a ref count and you panicked. Well, you're holding on to some resource and you're never letting it go, and the ref counts are greater than 0 and no one else can get it. So effectively you took a lock and you didn't unlock it.
Right, and so I'm of the opinion there it's best to just fill the entire program and then have a OS level monitoring system react to that in some way.
Yeah.
Which typically will be, restart it maybe 2-3 times, then keep it down and, send an email somewhere or something like that.
Watchdog timer.
Yeah. Because that is, at least in my opinion, the only way you can reliably catch all errors. Because if you have these in process, let's say, exception logging systems, but you would use them for panics, it's entirely possible that a panic prevents the logger from running. Okay, if it's a panic that corrupts the entire process, you can try to log whatever you want. It's probably not going to work. And so you wouldn't actually see it. You just at some point look at a graph and observe that your throughput is low, but you don't know why.
See, I would have said, it's not the example I'm looking for yet. Why does the panic corrupt a logger? You have a concurrent logger and the panic wants to write to it. I'm guessing.
No, so let's say every task has a when it panics, it runs a function, and what it does is basically take the panic, its stack trace, and send it to some external service to present it later. It's possible that based on whatever the panic did, it may fail to send the data, or perhaps it will panic again within that process. It depends a bit, what the cause is.
Logger interface to another thread.
It's not necessarily a thread, just it sends it somewhere else. So that might happen. Like, let's say you panic, you want to submit these details somewhere, and then it panics again. Maybe the initial panic was a memory error. You got enough memory that you can run the panic handler, but then it panics again.
Yeah. I've totally had to debug these things. And
right.
Yeah.
Basically comes down to kind of similar to sandboxing. Like, monitoring or sandboxing within the process itself is, I would argue, never going to be more reliable than monitoring or sandboxing external.
Okay, wait.
Okay, sandboxing maybe depends on what language you're building, but
I claim that in theory a sandbox could be perfect.
Right, it could, but let's say a simple example. Let's say you have a sandbox that you set a flag and you can't use networking sockets. Well, if your language is FFI, you can still use sockets, right? So you also disable FFI.
The sandbox has to say no FFI.
Right.
Well, it's not a sandbox. Same as Java has unsafe. If you use unsafe, you're not safe.
Right. But basically what it comes down to is that whoever implements that within their language, runtime or whatever it is, has to cover all the cases. And this is entirely possible. But I take the approach... Sorry?
I was going to say that I kind of agree with what you're saying, but I would maybe... I'm going to explain it a different way and see if this is what you're trying to say. Let's say that Cliff is right and you can have a perfect sandbox. I think what you're saying is, sure, sandbox could be perfect, but if something bad happens, there are going to be conditions, even with a perfect sandbox, where you will not be able to surface what bad happened, right?
Yeah.
And so it may disappear. It may disappear with the sandbox.
The sandbox has a border that lets things through that are whatever you've defined can cross the border. If inside the sandbox you're going down in flames, you're going to have some pipeline that legit things can be filtered out through the wall of the sandbox to I want to say, I'm going to use Cameron's concept here, but this works for OS as everything else. That you're legit taking out of the sandbox. You have to validate it because the sandbox can be a security trap. Someone's trying to hand you a honeypot out or whatever you want to call it.
But look at what Unix does. I mean, when it gets to a point where it doesn't handle inside, if you will, a sandbox, it says, I don't know what to do with this. Yeah, you can see it, but you can see it because it's a 64 gigabyte file that it placed in your home directory that you can later examine.
That was your export of your state. Now, if inside your sandbox you have a further error recovery mechanism that you're going to use to produce something as a cookie, as a useful message out, but inside the sandbox you got corrupted in any way possible, then all reporting might fail. So the best thing you can do is say, inside the sandbox, I make an effort, but it might fail. Outside the sandbox, I will get something out of it. Maybe it's my Unix process dump, 64 gig file. Maybe it's some polite error message that I will then validate is correct before I let it go on to the next part of the outer sandbox. And that's the limit. So I'm just going to give up within the sandbox. Now, when I say give up within the sandbox, maybe I'll make an effort to nicely report, but panic is death.
Right. I think it's worth mentioning there. It's not so much that you can't make the perfect sandbox container, whatever you like to call it. It's more that I don't trust myself to do it. Right.
Yeah.
So when I look at these panic handlers, for example, or sandboxing, whatever it is, I generally prefer to take whatever facilities there are from the OS because I trust they do a better job at it than I do. So with sandboxing, for example, I've occasionally toyed with the idea of putting some sort of sandbox in my language where you can say, oh, disable sockets, disable FFI, this, that.
This is the.
But I've kind of
process.
concluded there that, excuse me, I've kind of concluded there that I probably won't get it right, and that it's better to, let's say, on Linux, run the thing under a C group and restrict it at that level, because that has been, much more battle tested. It has more functionality. Etc. And this panic handling kind of falls in the same area. Bugs should just terminate because I don't trust myself to implement something that will always work the way people expect, that has to clear boundaries, etc.
So your programming model then says, if I want to run multiple parallel managed things, I'm going to throw each of the managed things in a process.
I mean, it depends on your use case. Let's say you have
there's some overhead. That's what's come around to.
Let's say you have some service.
That's sort of where Apache came from. They wanted to make sure that a request could fail without bringing down your web server, so they forked on every request.
Right. So that is different because, at least in my language, errors that you are expected to occur are statically guaranteed to not be unhandled. And the whole idea is that
we're not talking about errors that you're expecting to recover from. We're talking about around memory, Stack Overflowed.
Yeah, and those kind of bugs, basically, they only happen when your code is broken.
Yes.
Or the system underlying is broken. And I'm of the opinion at that point. It depends a bit on the panic, but you can try whatever you want in your runtime. Fat chance it's going to happen again. And if it's going to happen again, I'd rather let the OS handle it, or some supervisor, because it saves me a few hundred lines of code. And
you're claiming it will happen again is another way of saying there's no forward progress to be had by me handling it and trying again. It's just dead.
Yeah.
And we have to keep up leveling the issue until we come to a spot where forward progress can be made. And one of the forward progress options is, I puked out a giant error message and sent an email to the IT guy, hey, your web server's down.
Yeah, exactly. So it's a more extreme approach of Erlang's let it crash approach, whereas Erlang says let it crash at the process level, and it sort of expects that, and it has supervisor trees and everything built for that. I've taken the opinion that basically the errors you would expect to happen are statically handled, to a point where whatever errors are unexpected are an indication of just bad code, basically.
Mm-hmm.
And at that point, there's nothing you can do. It will happen again.
Right. In the land of H2O, when you wrote a broken inner loop function, you would get a range check exception, not once, but millions of times, all in parallel across your entire cluster. Every thread would hit the same exact fail. And of course, you'd have to deal with, you wanted to, that was broken, but there was no retry, but you wanted to have a sane error message. Yeah. Deal with a million errors. Is it down? Oh, here's something. Okay, there's a video. There's the whole is it down website. That's
don't watch that until you've got time to laugh.
Okay, fine. Yeah.
And
fine.
by the way, Matt, I'm really curious. What is your ID on Reddit? You're on mute.
You're muted, yeah.
So I'm 99% sure I know who he is, because there's someone who's constantly posting good links on Reddit. I'm like, this has to be that.
It's all good. He just logged in and,
I think it's MTT something, so.
I'm curious, Cameron, your thing has a lot of small isolates that can all fail. Do you have an equivalent of a core dump for one of those to say, hey, the entire thing didn't stop, but one of my isolates failed? Give me all of the state that it had at the time it blew up.
So you're asking me?
Yeah.
So we don't yet have that level of capability. It's just we haven't gotten that far.
It's got its
But,
own stack and its own heap. So in theory, you could like core dump it.
So basically, we have what we call a service, which is a domain. It's kind of a cell, if you will, in a multicellular organism. So it's got a cell membrane, and basically it owns what's inside, and what's outside it can't touch directly, right? And so that, yes, so we do have in a debugger right now, we do have access to all that information, but we don't have anything cooked to spit it out. And then, but we have a bigger concept as well, which is called a container, which holds some number of services. And a container, so while a service is equivalent to a domain of mutability, a container, its domain is defined by a type system. So transitively closed type system. So the services running within that container are all using the same type system. So, and where this differs from what Cliff did with C2 and Java is Java accidentally discovers classes all the time. Like, oh, here's something on the disk. I'll load that as a class. So, so your surface area is
that accident.
Yeah, no kidding. Your surface area is potentially infinite and yet to be discovered. And what we did instead, in no small part inspired by Hotspot, is we looked at the problem and said, if we can transitively close, we can predict a number of the things in terms of optimizations. And then if we need more than what we transitively close over, we can create a new container that itself will transitively close over a type system. So, so yeah, the goal is basically what you're thinking. We just haven't implemented anything like that yet.
Your comment about Java loading things off disk, just as a different perspective that you might take that considers the stuff on disk as just part of the system. Right? Like you can think of your Linux box and its file system. You're running stuff, some of which is on the disk and some of which has a copy in RAM, but it's all part of the whole system.
The Sandbox includes some amount of disk space.
Yeah, well, all of it.
Yeah,
So what?
as soon as you say all of it, then the OS itself is at risk because you just patch.
No, the OS is just part of the program that's coordinating all of this stuff, deciding which parts need to be in memory and which parts can be.
Oh, no. That declares your sandbox to be the whole process. And we're trying the whole hardware. And I think we're trying to define a sandbox to be a fraction.
Well, no, I'm countering Cameron's comment about how you got a closed world, except in Java where you can load things dynamically. Well, the world is just bigger than what's in the memory at once.
Right.
Yes, but you can close Java's world down by denying it new classes in a variety of ways. But that just, I'm sorry, I heard you say, think about the problem as everything you can see, including on disk. And on disk could be new code and new types. And as soon as you go, I'm looking at the whole of the disk, then your unit of safe recovery mechanism has to extend to the entire hardware box. But I can't reach to the hardware next to me without going through the TCP socket and an Ethernet cable. And the OS on that side guards it. So the unit of sandboxing that I have to recover a panic is just, I have to reformat this box because the virus came down and scribbled on my root disk, and that was the unit of fail. Whereas we're looking for a small unit, which is I have a process that the OS likes to keep separate from other processes, but if they share through disk, then I can have fails. This process can scribble something like run the disk out of memory, out of space, and so that process can't log, so his logger throws disk full, and you die because somebody's continuously filling the disk with log messages. How many of us have gone through that fail for years? So is there a way to isolate these processes in a sandbox that's perfect. I claim yes. Is it worth the effort? I don't know. Is the OS doing it now? Kind of close. In the case of, the infinite disk writing guy, you simply have to slice the disk off and say, with this process, you get an extra gig to go write your shit, which Amazon totally does to you. And if you write more than your shit, we blow up on you, but you don't get to blow up your neighbor. And so you know that this can be done.
Yeah, and Keith, let me. I should have put some more detail on what I was saying. So Java has this, and it's brilliantly done. So I'm not, I'm pointing out issues with it, but at the same time, lots of respect there. Java allows and Cliff can talk to the details, but allows the generated code to basically stop one level outside of its boundary of what it needs to execute. So for example, if you have foo that calls bar that calls dingbat, right? If you're compiling foo, it has to resolve some information about bar, but no further. And this applies to methods, classes, fields, etc. Like there's this concept, like there's what I've compiled that runs, and then there's kind of a no man's land that I know about, but I'm not actually compiling it down yet. And then there's stuff beyond it that you don't even imagine that it exists, right? So if someone then calls bar, it's never been called up to this point, but now it gets called, right? So now that no man's land is going one step out, right? And somewhere in that no man's land may be entirely entire jars that haven't been loaded yet that are in some part of the class path, right? And with Maven and that style of development, if you download say if you use say one class out of Spring, you accidentally downloaded 843,000 jars, and one of those is Apache.
You got it.
Right, and then someone can send you a malformed RMI message which mentions a certain Apache class, and then the Apache class looks for a string and then runs the code in that string, and then your computer is owned by someone else. So it's like that's what I was talking about. So even if your app doesn't use that Apache library at all, it's like beyond the no man's land, you could still end up having your server completely owned by someone who just happens to send the right formatted RMI message.
Rephrase my comment as, this isn't specific to Java. I think just Linux, you can have a program can fork and exec something else arbitrary that it just created or was on the disk last week.
Yeah,
exactly.
Yeah. And there are ways around what you talked about with Java to prevent that. But there are definitely, you can write code that conveniently stretches the boundary indefinitely. The usual story for me is I simply don't include that code, don't have any of those jars, and so I don't have any hooks that say, and also go to Maven and load again. That's not in any code I wrote. So not in any of the code I wrote. So I don't suffer that, but I have seen people get there. The theory is correct. There is no limit. You cannot define ahead of time. You can define ahead of time a limit in Java now that says this particular chunk of code doesn't add anything. Oh, no, you can't. You're right. The question is can I look at a wad of Java code and know definitively that I'm looking at all of it? That it will never class for name anything new that includes anything indefinitely ad infinitum. And I think there's no way to stare at a piece of code. Like there's no type system boundary. There's no container boundary like you have that says, and within this box, nothing more shall ever come again. And so I can look at the box before I launch it and say, this
so they're definitely getting cleaner about it. I mean, if you look at Brian's conversations on sealing stuff, for example, and the total, what he calls totality or whatever, where they're trying to prove that, for a certain type, they know what all the subclasses are. I mean, they're definitely working on that.
Yeah. Well, until you get the ability to name a closed universe you have the open universe issue, and kind of want to. You always want to I think you kind of want to always have an open universe somewhere at the top, but you always want to manage that piece. And you know, the pieces that you manage internally, you kind of want to not have an open universe on. As you say, it just gets, it can get crazy. I don't have a good answer there yet. My current theory for AA is I'm going to definitely have an eval as a way to do class for name, but I don't know what to do with bounds on it in terms of controlling its reach.
For your eval, are you passing in an environment that's like, hey, you can't talk to the file system because I didn't give you the function that lets you talk to the file system?
Yeah. So you get you get an environment, and the caller of the guy who owns the eval call can choose what that environment is. So he could, in theory, hand you a really tight sandbox, and then tell you go. I haven't figured out how to do like memory limits and or stack limits and stuff. You know, various resource limits let you do some, but not all. Here is the root of a fake file system that I'll hand in, and now you're relative to this root and you can't get outside of it. And whether it goes to disk or not is entirely irrelevant. You'll never know. It's just a convenient thing because you're an old school program and you demand a file system for your temp swap. Okay, fine, here you go. But it's a fake, you know, right? But there's a lot of work. This is a York thing. There's a lot of work to make that sandbox perfect. Right now, I'm going to start with you get an environment, and you know, and it's the current environment you're in minus whatever you're cutting out. So there's something that says hide all the functions I don't want to be passed along, override them with the empty error, whatever, and then call the eval. And really the eval is going to be two-step. Take a string and you get back a compiled function or an error that it was syntactically incorrect. But if you got a compiled function, if you call it, it does what it does. So that's still need some way to bound the limits there, the sandbox. That's a good one. Okay, what else?
So Cameron, this is a quite complicated system that you're designing. How do you intend to test it with all of these security constraints and resource management things?
What is testing?
Okay, so having some confidence that it works.
To be fair, I mean the model is the you know, first it has to work on the whiteboard. So for the most part, the design was done before the code started getting written, because if we couldn't prove it on the whiteboard, we knew it wasn't possible to write. So it's more a mental model that, you know, our code may be wrong, but the mental model was proven to hold by some definition of proven, which is, you know, not very formal.
But you haven't gotten, you know, the attacker script kiddies to come at you and see if they can break you.
Just one, and he's broken it 1,000 times.
Excellent.
So.
Because I remember that you had some fairly complicated resource management policies, like being able to allocate time, for example, and
right.
scheduling is always extremely difficult to test.
Yeah, those are not all implemented, but yeah, that's the API is in place, but the API and the statistics collection, I think, are both in place, but the full thing isn't done. And right now, it's a little easier to do it because it's an interpreter. So for a language that was explicitly not designed to be interpretable, the only thing we have for running it right now is an interpreter, which by definition sucks. But the real complex part will be translating it into runnable code, because there's a lot of things that are easy to do in an interpreter around life cycle and management that are incredibly difficult when you're actually spitting out assembly.
So there's a hotspot lesson there, which is don't do all the hard stuff. Keep the interpreter and bail out to the interpreter, and gradually over time, bail out to the interpreter less and less often. But every time you find something that's hard to do, bail out. And then you grease the bailout path and you fix it and you find all the bugs in the bailout path. But once you get that combo going, you can now incrementally improve the compiler and the runtime around things that are too slow to only bail out to the interpreter rarely and ever more rarely.
What is the advantage of that over a templating JIT that just generates really dumb code for the sort of base case?
Yeah. Templating JIT is a version of an interpreter.
Correct. That's what I was going to say, is we're not planning to do an interpreter, but we'll use something akin to a templating JIT as our default ugly.
You have to have a first level, lowest level, guaranteed will execute. And whether you use an interpreter or a templating JIT is sort of, I've done it both ways, 6 one, half dozen the other. They both have their pros and cons. The interpreter has a much harder calling convention to deal with. It has, but conceptually, there's no code gen, so it removes a big problem there. Like you can write an interpreter entirely in C as a high level language, and performance won't be the best for an interpreter, but it's entirely tractable to debug and develop in and understand. As soon as you do any code gen at all, you open up this giant can of worms that you have to deal with for a while. Well, but you can deal, and the templating JIT's not very hard, and as long as you keep it a template and you recognize that your intention is as a template, because if you incrementally begin adding more and more performance to it, what you discover is the template JIT sucks as a way to do an optimizing compiler. It's a really bad framework for doing an optimizing compiler. So you shouldn't actually try very hard on it.
It's the only thing a templating JIT does is gets rid of the while. It
gets rid of the dispatch.
While one loop. Yeah.
Yes, gets rid of the dispatch loop, which is typically half of all your execution time in an interpreter. So if you do a templating JIT and you do a little bit of template folding at the edges, which you kind of can do conveniently, you can pretty much yank all the dispatch costs, and it's like twice as fast as a good hand-rolled assembly interpreter. Like I've done this a bunch of times. This is like, I wrote a C interpreter. I wrote a C interpreter using GNU label vars, computed gotos. That's like twice as fast. I wrote a hand-rolled assembler with hand-rolled dispatch logic. That's twice as fast. I wrote a template JIT. It can be 40 to 70% as faster than the interpreter, but it doesn't get too much faster without really getting heavy on the optimization. But it's a lousy framework for doing optimization in. And it's harder to write than the interpreter. So I find that these two are kind of a sweet spot. This one's a little overhead to get started, a little higher on your lowest end execution.
But you did make a good point earlier, which is that the calling convention is part of the benefit of the templated.
It is one of the benefits. So I fixed the calling convention for hotspot. I'll tell you how to do it. It's a pain in the butt, but it's tricky. But you don't have to deal with it with a template. And that's the signature. The calling convention is all about the signature, the function call, the caller versus the callee. Everyone has a different layout. Your language probably wants not the C calling convention because C has varargs to deal with. And if you're strongly typed, you don't have to deal with varargs and life gets all simpler. As soon as you have an interpreter.
And we have multiple returns and yeah.
Yeah, right. Okay. So you have a little function in life who takes the two signatures, the in and the out signature, and it produces a stub that just does the argument shuffle as a piece of machine code. And you can write this in a big ass piece of C code that's 2 to 5 pages long, does all the cases, and just emits assembly in a buffer. And the assembly in a buffer is just a register shuffle. Okay, given that as a toolkit piece, you can now cross call between interpreted and JITted and templated and native FFI reasonably easy. That's a big chunk of it. You still have all the runtime issues to deal with guarding your stack and garbage collection and locking or not locking, whatever safety things you do around the different things, and how to handle exceptions as you cross between its interpreter frames and compiled frames, and that's not solved. But you can cross call by doing this stupid little hack, and it takes some of the pain out of the template JIT. The template JIT doesn't need it because you don't deal that way. And if you pick a native C calling convention, then you can do FFI without also screwing with args again, but you don't get sort of the optimal self-call to self-call calling. Like Java's performance is, I have the optimal JITted to JITted calling convention, and I make everyone else pay. So all transitions to FFI or the interpreter pay. but JITted to JITted code is the best I can imagine it would be. That was the design parameter we started with. And having said that, we also started with an interpreter for historical reasons. And having looked at that and having done a template, I would have said they're pretty close. Template has definitely got some conveniences over an interpreter.
What was the, what did you find in terms of code size, in terms of impact of code size from the templated JIT?
This was back in the day, and yeah, you had to deal. You blew out iCache. You could template pretty quick. x86's iCache is much huger now, and its path to L2 is much bigger. So the numbers are probably better. One of the games, there was definitely an era where the templated JIT that we ran around with in Hotspot for a little while, compared to the interpreter, once your iCache got big enough to swallow the interpreter, with I and D, but not the templated JIT's template code, the interpreter was faster. Despite the fact it was clearly had more dispatch logic going on, a lot more instructions, endless iCache misses for the template. These days, the shoe might be another foot. That's what I'm saying. They're probably pretty close now. If your low end guy is plus or minus 50% over what you could imagine the low end guy to be, I think you're fine, because once you step to a real JIT, you should expect to see 5 to 10x speed up. So you don't want to burn like a 2x improvement on your low end guy, but he's 1% of your execution time. You don't care. I have a new guy I don't recognize. Maybe.
I think it's worth mentioning there, like probably a benefit of interpreters over templating JITs is that you don't have to deal with code generation for different platforms, assuming, of course, that the language you write your interpreter in is portable. That's, for example, actually why, well, at least one of the reasons my language is interpreted, because when I started this, and still to this day, there aren't really good libraries for Rust for fast code generation that supports more than x68. There's, of course, LLVM bindings, but I have long since decided I don't want to deal with LLVM and all the different versions across Linux distributions and their 15 JIT APIs and whatever.
For Max's benefit, we're talking about the lowest level execution for a language, where your choices are interpret or a template JIT, or a C interpreter, assembly interpreter, template JIT. And this is not the high-end JIT. And what do you have to deal with to deal? And there's cross-call issues, and templating JIT lets you have a good API to call your high-end JIT. Whereas an interpreter has a lot more easy setup and go. You don't have to do any assembly at all. Although if you do assembly interpreter, like I said, you can get like 2x over your best possible C interpreter. But maybe you don't care if you have a good high-end JIT.
Yeah, so it was, for me, it was basically LLVM as an option. I guess you could. Sorry?
I've watched LLVM. I've been looking recently at Julia emitted code for LLVM, JITted LLVM. And there are some interesting performance potholes because it's LLVM, doesn't include a runtime. So go first, and if you want, I'll step you where LLVM can't do it.
So as LLVM, I did briefly consider compiling to C, but then you'd have to write a substantial part of your runtime, at least in C, and I'm just not comfortable with doing that. Compile to Rust. Rust is too slow to compile, so that basically eliminates it immediately. And that basically means you have an interpreter left. Nowadays, there are some JIT libraries. There's a library called Crane Lift, which is completely standalone written in Rust. But last I checked, it only supported x68, and I think they only recently, as in like the last year or so, added support for Windows. So it's still in the, I would say, very early stages of being a mature library, and it doesn't have any optimization passes whatsoever. It's just a fairly straightforward take a IR, compile it to native code. That's it, basically. So I ended up writing an interpreter for it. being able to piggyback on whatever Rust supports. Granted, it's 64 bits in my case. But yeah, I will probably have to add a JIT at some point, which on the one hand, I kind of acknowledge that that is going to be necessary. On the other hand, I'm like, I really don't want to deal with that because you have to a certain extent, duplicate logic from your interpreter loop into the JIT. And it's going to be these subtle little differences where you have to be very careful so that it doesn't end up doing one thing when it's interpreting while doing a different thing while it's running JITted code.
And for which
Yeah,
you'll
but-
probably have to clean up the semantics of your interpreter a fair amount, which
Yeah.
will change your language semantics until you nail it down. Yeah.
I mean, there's a simple example right now because the runtime I have is preemptive. The quote unquote registers are basically implemented as just a vector where each register is an index to it, which isn't particularly great for performance. But there isn't really an alternative. But then when you have a JIT, ideally, you put these things in actual registers. And so now you have this difference where it's like, oh, if we run in JIT, if we run in interpreted code, you have effectively infinite number of registers. But then we have JITted code, so we need register allocation. And I have to do for different platforms, wanting things in different registers. Yeah.
No, it's a
I'm not
good
ready
start
for that.
though. I mean, you start with an infinite number of registers, and then you let a later pass map those to actually registers or stack or whatever. You know, when you're emitting
Right.
code. I'm kind of
Yeah.
hoping. So the design we had, we built our own IR, but the idea was that we would have build a custom library for interfacing with LLVM that would allow us to introduce both hooks into the running code, so the running code could call us and say, hey, I need more code. I hit this slow path that hasn't been filled in yet, for example. And then the flip of it is some translator from our IR, because LLVM has two fundamental models for emitting code. One is you can give it LLVM IR. The other is you can actually drive the LLVM, I'll call it an assembler. I don't know what they call it. But you can drive it directly via API, or you can give it IR. And so what I was thinking of doing was basically just producing a representation of the LLVM IR. We already have a representation of our own IR, and then you have the compiler per se just translates one to the other. Translates is the wrong word. The compiler forms LLVM IR out of our high level IR.
Yeah. It's a
And Matt gives us IR builder.
Yeah, so my rough idea, and of course this is going to change completely when you actually implement a JIT, but the rough idea I had was to have the JIT actually do as little work as possible. Basically produce bytecode that at least has the more expensive optimization passes already applied. Because what you typically see in interpreted languages that they spend quite a bit of time just JIT compiling and optimizing, and then perhaps the total runtime is short enough that perhaps it wasn't all worth it.
So maybe here I should chime in. If I look at where the time goes in the hotspot JIT, 50% is in the register allocator. The high level optimizations like loop invariant code motion, loop unrolling, range elimination, tiny amount of execution time. They take nothing. Totally worth it to do, take no time. The IR being optimized for doing optimizations takes a quarter or a third. So like a quarter is probably parsing, which is complicated and includes a lot of inlining decisions. And a quarter is all other optimizations that you would classically think of, all your dead code, common expression elimination, loop invariant code motion, all those things, they boil into a quarter of the time, but most of them take much less. There's not a whole lot of time in there. And then the register allocator. So
Yeah, I figured a register allocation would be quite
But-
expensive, and so
right, what it
I
means
thought
is,
about doing that perhaps at the bytecode level. But then you have this challenge where you would have to generate bytecode that targets the lowest common denominator. Now, as far as I know, most platforms have similar number of registers, but there's always going to be that one person that compiles it on x68. I don't know, let's say you have 32 registers and they run it on some platform that only has 16. So yeah, I'm not sure yet how to deal with that.
well, I'm claiming you shouldn't be trying to register allocate in a bytecode format. Yes, 32-bit versus 64-bit. They all have all the registers now, I believe. It's just whether or not you get to use the upper half. No, don't bother doing register allocation in bytecodes unless you are targeting a template JIT, where the goal is it's pre-allocated and the template JIT's going to optimistically use the pre-allocation if it works, right? Only JIT unused pass nodes the other way around. Only JIT hot paths, and go to your lowest level execution for your cold paths. I mean, that's certainly what Hotspot did, and life got hugely better. We didn't try to JIT everything, but as soon as you make the hot paths cold enough, more and more things become warmer in relative comparison. So you do have to do not just the inner loops. You have to include a bunch of the surrounding stuff. No, I was trying to say, if you're trying to come up to output from whatever your language, something you can execute and something that you can JIT, and you have something for the template JIT/interpreter, and you're going to feed it also into your high-end JIT, give up at the high-end JIT, give up trying to do register allocation. That's a problem to be solved by the high-end JIT, who will know how to do deep register allocation issues, including registers that are special to this hardware platform only. The version of x86 has different registers every time. Have more or less cost to use different registers, shit like that. You don't want to deal with that at some sort of semi-portable way. Yeah, pull that one out for Hotspot. I've done that work for Hotspot, and the converting bytecodes to IR was extremely cheap until a bunch of people piled in, because we turned out we had to deal with code that wouldn't pass the verifier, and internal bugs with linking loading constraints, and all kinds of weird shit happened there. And then the IR generation got uglier, and inlining has to happen for Hotspot early, way too early. If it happened later, nowadays it can happen later, then it makes more sense. So building instructions, building SSA form from bytecodes got expensive for no good reason. But like I said, it's about 25%. Register allocation about 50%. And register allocation's where you reliably get the most performance once you do all the easy shit. Like you have to do loop invariant code motion. You have to do range check elimination if you're going to have range checks to be dealt with. You have to do a bunch of things, a common sub-expression and folding null pointer exceptions. And these are all relatively straightforward, relatively classical C compiler-ish kind of optimizations. You just do them. Once they're all done, the next highest order bit where performance comes from always toggles back and forth between better inlining and register allocation. You inline too much, the register allocator blows out. You inline not enough, you lose the overhead at the call boundaries. You lose the knowledge, right? So I reliably would, for many years in Hotspot, I would reliably go tweak the register, tweak the inlining heuristic to get more stuff in, and then tweak the register allocator to not fail so badly. And I would get 5% for everybody. All your junk Java codes across the planet would get 5%. You could go beat on HPC codes and get a 2x for some hot Fortran loop, but no one ever cared. You wanted to make JBoss go faster, web service go faster. You wanted to make Apache Spring, whatever, go faster. It was always inlining and register allocation. Those are your two big hammers.
Do people ever build interpreters for low-level IRs as opposed to building a JIT for every platform?
Well, I think that's what we're talking about. They're trying to decide what level you make the IR that you're going to interpret.
Yeah. But that used to be very common. So Microsoft, for example, that's how they started their business. They had built a low-level interpreter, and it ran on a couple different hardware platforms, so that the code that they were delivering back in the 70s
Yeah.
was mostly interpreted.
Yeah. Visual Basic. Oh no.
Visual Basic came out of that, but originally it was BASIC. For example, AppleSoft BASIC was written by Microsoft.
Yeah, boy, that's even going back further. Sure enough.
Yeah. So Apple tried replacing it with their own, and Bill Gates just held up the license agreement until Steve Jobs killed the internal project. Actually, that was one of the one of the first times that we got to see Bill Gates at work.
Yeah, this is the guys I'm doing consulting with. That's where they're at right now. They have an issue that LLVM's so slow. They're compiling every query down to LLVM code, and overheads are killing them.
Yeah, it's a relatively inefficient JIT,
Yeah.
but a relatively decent AOT.
Yeah. Yeah.
And the benefit of LLVM over most of the other options is that most of the other options were written 20 years ago and nobody's maintaining them.
Oh, I see. Well, I tell you, LLVM's got some ways to go, though. But
Yeah.
they don't have any runtime, so you can't do things like.
But there are 10,000 people working on different parts of it.
Okay, fine. There's still no runtime, so you can't have code calling JITted code. It has to bounce through a patchable, a load call sequence instead of a patched call, which is an x86 hardware blip every time.
Yeah, there are some other JIT libraries. Like, it's true, there's a whole bunch of them that basically aren't maintained anymore. I think GCC now recently they had a JIT based on their library, but then you have to deal with GPL. There's one called, let me look it up. I think it was called mjit or something like that. Or was that the Ruby version? Either way, it was this JIT library where I think originally developed for Ruby, and I think it was JITting by originally compiling to C, but then they added like a proper JIT. That might be confusing too. No, sorry, Ruby has the one where they compile to C, and then there was this replacement library for it. See if I can find the name for it in a moment.
I think there's two projects called mjit, which is why this is confusing.
It could be because I think one was from some Eastern European, a person with an Eastern European looking name, but that's the only reason I remember it. But I can't find it now. Maybe I have it saved somewhere. But either way, that one looked interesting because it claimed to have fast compilation and a simple API, etc. But it was like a one-man project, basically. So there's no... Oh, Mir. That's what it was called. I found it. Let me share it. Oh, yeah, there we go. It's from the, I think... Oh, wait, is my internet working? There we go. Maybe they're the same people. This looked interesting. But yeah, it's one of those things where it might not exist 2 years from now.
Yeah.
And I think a JIT is complex enough that you don't really want to spend months implementing it and then have the maintainer go, you know what, I'm not interested anymore. I think one of the more interesting ones I came across was a project called Holy JIT. Don't think I have to explain where that comes from. But it was this project where people extended a older version of the Rust compiler. Sharing the link. And you'd have to annotate your interpreter loop in a certain way, and then it would generate a JIT accordingly. I never tried it, so no idea how functional it is, but that project too seems to have stopped. But it was an interesting concept because I believe it promised to have, let's say half the performance, but only for a fraction of the work. but unfortunately, it's not really actively maintained.
So an Apple is now pretty much using LLVM for all the toolchain work on the compiler side, as far as I can tell. I'm sure there's someone in this meeting that can verify that, but they're also donating a bunch of stuff that they already built back into LLVM as well. Azul uses it, right, Arthur?
You mean LLVM in general,
Yeah,
or some the
LLVM.
Yeah. So Apple is one of the biggest contributors. Yeah.
And Intel started this past year contributing fairly heavily as well, which is not surprising. They've always been involved in every compiler toolchain that they can because it gives them benefits in benchmarking when they can sabotage their competition. I mean, when they can provide access to their new instructions.
Been there, been on the wrong side of that one already. We caught them with their hands in the cookie jar, cheating on a benchmark. way back in the day, Motorola PowerPC versus x86, and their compiler was pattern matching on a function name and then emitting code that was not correct for the code in question based on the function name. So if I changed the body of the code very slightly, they would emit incorrect code. And then
well, it's called intensification.
Yeah, no. It would be intrinsification if they simply pattern matched the code. And
no, they intrinsified the benchmark.
They pattern matched
intrinsification of the benchmark.
They pattern matched the name of the function. That was an insufficient pattern match. Long time ago.
It sounds like programmer error to me.
You couldn't do it with the knowledge available to you of the function in question, the transformation they were trying to accomplish. It was only valid in a larger context of much of the other benchmarks surrounding it to get enough information to make it correct. You could make a transformation that was reasonably close that they should have done, that would have lost some performance and given up the top, that they cheated and got like 30%. They could have not cheated and gotten 20%, but they didn't even do that. They just pattern matched the name and slapped out some code. And some hotshot programmer said, well, this is legal. It was only legal if you could investigate the surrounding context, because otherwise you had 16-bit integer overflow issues that you had to assume were correct or not, or whatever, that you couldn't just do what they were doing. Whereas if you just pattern match the code, you could do a horrible evil hack that would get you could legit by looking at, I don't know, this guy and a couple of inlines, and it was fair enough, which is what I ended up doing. But at least it was correct if you hacked the code around. But you couldn't do the thing they had done all the way unless you had sort of an oracle thing that read the entire benchmark. But then, like I said, they didn't even do that. They just looked at the name and slapped out broken code.
Well, we talked about a similar example before in these meetings, how Graal trusts the content of some fields, just looking at their name and saying, well, Java C generates this kind of field for switch by enums. I will trust that the content of the array will never change.
Oh, but you can security hole in Java and change it easily.
Oh yeah.
God, does it still do that?
Well, the last time I looked there, it was in the code. I don't know if it was fixed or not.
Yeah, fine.
Yes, it's still there. So there's an internal issue for that. They will fix it, I guess, in the right way, right? But no, it's not fixed yet.
Like the right way is you can't trust it, and that's a big performance hit. It's because the enum API is stupid. But you have an API you can't make go fast legitly. Yeah, inline final fields. Yeah, I tried that one too. There are a bunch of major frameworks that would use reflection to change final fields. And if you talk to the developers after I discovered this, they would say, yeah, we know, it's kind of a screwy thing. And it's like, okay, what do? You get complete, either kill a major named benchmark, 3 major named frameworks, or you don't do final field optimizations, or you certainly limit them.
Or you do it through dependency tracking and de-optimization if this thing happens.
Yeah. Eventually, I had to decide that final was not the actual final. It was right. I didn't get there. That was the next step, was to say, I have a field that is rarely written, read often, written rarely. I'll treat it as a compile time constant and ignore the final flag. It's just every field that is rarely written and read often, I'll treat it as a final until it's changed and track the changing on it. And that would have been a much better optimization than doing anything with final fields, which, as I said, were not actually final.
Yeah, that's what we eventually did.
Yeah, okay. Yeah, that's a good answer. Did you get any numbers out of that? What was the performance gain?
There were some gains. I don't remember any numbers right now, but there was a talk on JVM Language Summit, and there was a slide with data. But there were non-trivial amount of workloads which improved.
Do something with, yeah. A lot of these planet fields are either ever always zero, or they're flags set at like start of the VM or start of a library or whatever, and they're never changed, and they control some high level thing, which you could then fold away. Cool. So back to your LLVM or not the LLVM question about what to do with your bytecodes. There's a faster way to JIT than what LLVM does. I don't know why they take forever, but they take forever. But doing the high level optimizations like loop invariants and things like that probably won't make LLVM go faster. If you're worried about code JIT time from LLVM, I don't think that's where they're going to spend your time. Or that's where they're going to spend their time. Somebody was saying they had it back in instruction selection. Really? This is from Matt. Back-end time is slow. Like not register allocation, but instructions. Like for x80 for hotspot, instruction selection is one of these one pass, one clock per node in the graph, done kind of stupid things. It takes no time at all. Scheduling takes a little bit of time, but doesn't win you a lot, so you don't try very hard.
Well, I would say that the ratio of different parts depends on the pipeline. And in our case, we have much more heavy middle-end optimization pipeline. That is why the back-end part for us does not take as much.
In a relative sense, it doesn't take as much. Yeah.
In general, I agree that if you look at the profile, it's fairly flat, and usually every single optimization does not contribute that much. So you can say that as well. It's cheap to do this, but altogether, it
adds up. Yeah. Okay, so it is possible to do all the middle-end optimizations really quickly, and instruction, especially on an x86, actually on everybody. And an x86, horseshoes and hand grenades, close is good enough because of it's so wildly out of order. And for everyone else, instruction selection is like trivial. There's only one way to do it, and it's the obvious way. And so you just do it the obvious way. It should be done fast. And then the same thing for scheduling. Most folks don't win all that much, and x86 wins even less because horseshoes and hand grenades, they're just so wildly out of order. Close is good enough. You just standard list scheduler and you're done. Excuse me. So I don't understand why the backend, those parts of the backend should take hardly any time at all. They certainly didn't take any time for me, but I had all my numbers were much, much lower than LLVM. The hotspot JIT is like 10x faster. It's hugely faster than LLVM. So the ratios, it doesn't make sense to compare ratios.
Yep, 10x sounds just right.
It's 10x faster, but doesn't it produce code that's like 10% slower?
No. Well, you can talk to different people. My experience is it produces code that's almost directly on par.
Well, at this point, I would say we comfortably beat Oracle C2 and Zing C2.
Okay. By how much? On what kind of things?
Well, we track about 400 something loads. Compared to Oracle C2, we have about 10%, which are worse than 10%. So and 90% are either no more than worse, 10% worse or better. And we have pretty big part, which is noticeably better, like 50% or more.
You should come up with those numbers. There's like a bell curve, and you can show.
Yeah, we visualize it as S-curve, where we take all the loads, take the relative score, and then sort it in ascending or descending order.
You get like a geo mean or just an arithmetic mean?
If we look at the geo mean, I think compared to Oracle, it's about 40%.
Yeah, that's pretty good.
And like we shared these graphs on in different talks. Like they are, so like it's somewhat older numbers. I'm not sure if I can just share what we have right now. Probably I need to check before I share it publicly. But like overall, that's 40% geo mean.
Yeah, if y'all can make a website that just shows the nightlies every night, that'd be cool.
Yeah. Yeah. Well, you have to, that's public knowledge. You have to get past the public presentation. Yeah, I'd be interested to see what was going on.
Like it is at the cost of 10x compile time. Yeah. But
but anything that's getting 40%, I claim C2 should be able to do with relatively low extra costs. But I don't know what the hell Oracle's done with C2 for the last decade, right? So and Zin comes on and tries to do string queries, and he's doing it the string optimizations. He's doing it the obvious wrong way. Or maybe he's not now, but he was doing it the obvious wrong way. If that pattern has been going on for a long time, then C2 could have been run downhill a long time too. There's an obvious thing to go do there. So I don't know where you get these kind of numbers out, and I'm curious to see where they come from. And
inlining.
Well, right. So the inlining could be improved in C2 when I left 20 years ago. I assume it's been improved all along, but I don't know. It could have been deproved, right? So and actually I do know that like Scala-like workloads have showed up a lot more than when I left, which want different inlining patterns. So there could just be some more dramatic inlining issues happening that could put a big push on Java as it stands right now.
Yeah, well, one of the big differences is that we do iterative and late inlining. We optimize and inline, then optimize and inline, and this is a significant difference.
So C2 was not doing that when I left, and I hear rumors that it's on or off by different folks, but I don't know. But it's the obvious right way to do it. It just wasn't done that way back in the day because I ran out of time. Somebody else did inlining at all. They did it at the bytecode level, and I took and ran with it. And then I was like, no, but we actually have to do something afterwards. And they're like, no, we can do this and this. And we did a bunch of hack after hack, but no, you want to do it afterwards. You want to blend the two. Okay, well that's good to know.
Yeah, escape analysis also a big thing in terms of performance.
Yeah, and like I said, I did a bunch of that at the Azul, but that was sort of half finished and not completed, and it became much more important after I left. So again, Oracle claims they're doing something there, and I don't know. Yeah, the you want achieve, not archive, maybe. Right, there's this cheap way to go blend inlining and optimization that's very obvious in C2. And that's just run the iter pass. And when you hit a call, you can inline, and you decide that at that time it's cheap, you inline it right there. And then you run the iter pass a while, and then another call will pop to the top. It's all obvious. The other one is
thing we do, for example, we do simplifications on inlining candidates. So we would parse the candidate, we would simplify the candidate, would inline into the candidate, and then consider it for inlining into the top level method. And it does cost, like if we end up not inlining it, we just wasted this compile time. But this results in a better representation of the candidate, and
here I'll claim I don't buy you that works compared to what C2 would normally do. What C2 would normally do is say, I have a bunch of candidates. I'm going to start inlining them one at a time based on whatever I decide to go inline, where it's hot and in a loop and whatever productive constants. But just nothing more than a very surface treatment. Inline it. But now the kind of thing you just said, where we clean up the candidate, the full power of the C2 optimizer, which is very fast. This is the middle end, is very fast. does that clean out. And if it turns out it was not very productive, the register allocator doesn't care that you have extra shit in there, so it didn't hurt anything either. So that's the different philosophy on inlining decisions. The optimizer is fast for doing sort of core gut simplification. It's fast and it's cheap. So you just inline and let the optimizer clean it out. And then the register allocator is tolerant of extra shit you've inline, and it's sort of a faster overall path to a solution. At least that's where I was at 20 years ago, even up to a decade ago. Seemed pretty clearly still, I haven't heard anything that changed that behavior.
Yeah, saying that the way the rest of the system is organized, over-inlining is just like not that expensive. So you prefer to over-inline.
Yeah, and you should inline in the middle during the optimizers, what you're doing with Falcon there, because you get more facts to guide inlining. C2 always did the inlining early. That was a mistake. Yeah, you're limited to inlining things that you knew at basically what you could get out of the bytecodes.
I would say we have to be more careful with over-inlining because there is constant tension between compile time and how much.
So the cheap, faster compile, so it doesn't have so much tension there. That's the interesting trade-off. Fine. Yeah, I hear you, Zen. I would claim that there's fewer passes needed in C2, so you don't make a pass. Like LLVM, it's easy to develop a new pass. I say in C2, you don't ever make new passes. That's not how you do it. You add a new graph rewrite rule, but you don't make a pass. And a graph rewrite rule is much cheaper and much simpler than a pass. All right, see ya. Oh gosh, there we are, 11:30. So that's a different philosophy as well. I've been through compilers that did pass after pass after pass. I did a couple of them, in fact. A lot of tension between one pass not doing things set up right for the next pass, so you have to run it again or whatever. The one big pass, don't add a pass. Add graph rewrite rules. That's the different philosophy there. All right.
Which is interesting. So the optimization Zin is trying to do, we actually have all the infrastructure at this point to do the same. It's just one rewrite rule for the escape analysis we have, because we keep track of symbolic states of allocations, so we can see that, okay, the source allocation we are reading from, it's initialized from another array. We know that alias and fox hold true. I think I should just go and do it sometime and see.
Yeah, but not right now. It's already 11:30, but I think that'd be cool. You can do it next time too. Yeah, C2 has a graph rewrite rule. I did it at Azul. Did a graph rewrite rule for doing a bunch of those escape analysis things. A set of graph rewrite rules, one after another, but a limited set. I'm sorry, Zen, you were about to say?
Can you hear me?
Yeah,
my mic is back. Sorry. This, you just mentioned that you should never write a pass in C2 because you rely on the ideal rewrite rules to do some kind of p-hole optimizations iteratively, right?
I rely on the
local rewrite rules.
Hang on. I rely on the iter pass being a lifting pass with local peepholes to remove a phase ordering problem between compiler passes. Yeah. That design removes all phase ordering issues. I get the benefit of running every possible pass over and over again to a fixed point in one shot with the design I have. That's why it's there.
Yes, so that's why I feel that in C2's code base, GVN is not just a global value numbering, it's an engine of optimization. So actually, I feel that the name is kind of like misleading, because I told you that I spent like a whole year to understand that, okay, this GVN, this class face GVN is the core engine of all optimizations, not just for global value numbering.
Yeah, it just started out as the deal is the graph rewrite rules are tied to the piece of the graph that we're rewriting. So they're spread throughout the nodes in the graph. So they're not a standalone thing, whereas global value numbering has a hash table for the global value numbering. And so that's why it's there as a separate pass. But global value numbering runs concurrently with all other peepholes all at the same time. So I just lumped the management under GVN, but the management process could be under another name. The GVN does something very specific. Hash into a hash table. If you get a hit, you win. That's the specific thing out of GVN. Everything else is under there for management. And so maybe you're right. The naming could have been better.
Yeah. We came from like a traditional compiler things like LLVM, right? So comparing to the C2, LLVM is like more like a textbook. So if we are talking about like the advantage implementation of compiler optimization, that's the classic textbook. So you can see that there are like hundreds of different optimizations. And, you write a compiler like a driver to organize them and maintain a certain order to optimize pass by pass, phase by phase. And C2 is kind of like different. I feel that you have like a single core, single engine. You see that you maintain the work list on your own. So I don't care. I don't take care of that control flow. I don't care about the certain order. You maintain the work list, and if you give me the right, interesting nodes, I will guarantee give you like a more ideal code. So this kind of like architecture is kind of revolutionary. I don't know, for me at least. I never seen code a compiler like this before.
So about once a decade, I find somebody who's never seen or understood how a work list style C2 graph rewrite rule compiler goes, and it's an epiphany. Yeah, it's very different. And once you get your head wrapped around it, it works out great. I don't know. I found it very easy, very obvious, but fine.
But then I would say that conceptually, for example, we do something very similar with iterative application of the same pipeline. Like it is the same like fixed point, and we need to do some like cleanup, like one transform open opportunities for the other one, and then like there's another opportunity in the first one. Like it's just how you drive it. We have a pipeline, like a pass manager, which does this fixed point iteration. You have this work list mechanism. But conceptually, you need to do the same thing.
No. It's asymptotically more efficient. It's fundamentally different and asymptotically more efficient. That's the difference. I guarantee you that I'll get everything that you can ever get in your pipeline in one pass on average, touching every node a constant number of times. And that is not the case in the pass after pass after pass approach.
Well, conceptually, it's fixed point iteration of some transforms. You have a more efficient implementation of it because you would not redo the whole pass and the whole function. You would redo things which you put in the work list.
Yeah,
I agree. This is more efficient, but conceptually, it is fixed point iteration of set of transforms.
Okay. So we're getting closer now. So it's conceptually the same fixed point, except that it's asymptotically faster because I don't have to do an order in operation to go visit another pass. I do an order one instead of an order in operation. However, that only goes up until you hit optimizations which fundamentally reshape things, and then you can't do it with pass after pass after pass. So any of the optimistic optimizations that run around have to start from a different place. And if you have more than one of them, then you lose because you can't get them without being optimistic over the whole set. So there is another place where it just flat out wins, but now whether it wins by enough be interesting, better inlining works better. So if you want to go into the heavy theory, I'm happy to pound it down. There's the optimistic side of things here.
And you are talking about what was described in paper, combining optimization, combining like analysis.
Yes, but you can do that at different scales. So anytime you have a thing which you can see in one pass You have two things. You can see one in one pass and one in the other pass. But to do something between the two, you have to see them both at the same time. You can't get
okay,
it.
I agree.
Okay. Okay.
Yep.
That doesn't require the whole program thing, which is what combining optimization is about. But combining optimizations is just simply saying, I'll do it in an arbitrary large framework. So that's the bigger hammer. The local people rules all the time do things that blend some combination of loop invariant code motion and or blend dead code and or three other things that you can't get by doing a pass after pass, but you have to only do it. They do an optimistic thing, but on a local piece of the graph, because they can just pattern match an obvious thing. So loop invariance is one of the big ones that happens all the time.
I agree that in theory, this has more optimization power. I haven't yet seen it in practice where this is what prevented us from beating C2 scores.
No,
So
better inlining. Better inlining.
Well, yeah. There are other aspects which would give you more, probably. So, but I agree.
We could sit down with small pieces of code and push them through the two different compilers and see what they come out with. This is a thing that I used to do all the time when I was looking at what I was getting out of other folks' compilers versus C2. And you kind of say, what do you do about this? What do you do in this case? This is sort of getting nitty gritty of where your compiler optimization can and can't win.
Yeah, I do have cases like that. When I'm working on some optimization, I often come up with if only I had this fax available here.
Right.
So I understand, yeah. So
all I'm saying is the iter thing gives those facts to me, because eventually they come. If they're ever going to come around, they come around. I don't have to screw with phase ordering or rerunning things to a fixed point somewhere else. The fixed point's already there. There is one fixed point loop. It's the main work list loop, and it gets everybody. That's fine. All right. We're well past due date here. But actually, this is kind of fun. If you want to bring around some presentation of where Falcon's beating C2 and what the inlining issues are, I would love to see that.
Yeah, I will go and ask whether we're okay with sharing the internal perf data, and if it's fine, I'll bring the data.
Well, even if you can't share like the overall, if you can share instances where you can show that there's obvious something to be done here, that C2 is blowing it, and then we can go sort out what happened and why, right? Where it did and didn't happen. So you're quoting pretty big numbers. There should be some cases where it's pretty obvious. Hey, we failed to inline here, or whatever, and had we, life would have gotten a lot better. And just sort of getting into the nitty gritty would be fun. All right, fine. Yeah, go ahead.
Kind of performance data is always very interesting. Like 10 years ago, GCC community posted a blog declared that GCC compilation time is 10 times faster than Open64, and some guy in Open64 just take a look at the blog and find out, okay, because GCC uses dash pipe, so they don't write the intermediate files to the file system. They just pipe those intermediate files to another stage of process. Open64 can also do that. Just a single line of code can catch up the performance. Yeah, the thing is, if we spend some time to debug, to figure out the root cause, sometimes it's very easy to catch up. But I'm not saying that C2 can do that to Falcon, but I'm saying that compete is always good. Competition is always good, because if we compete each other, we can get better and better.
Better for everybody.
Yep.
Yeah. All right, I'm going to call it in here because I've been on the phone since hours and hours, and I'm done. Until we meet again next time. It was a good conversation.
Bye, guys.
Bye.
Bye.
Bye.